welcome back. Today's goal of this lecture. In my previous video, I had seen what is the identity theorem. And I had seen some more example about identity theorem which had come in different type of competitive exam. Today's goal of this lecture, today I will see some more concept about identity theorem. Because I have told you more times, identity theorem, this is actually very conceptual for higher study. At first, just as a review, just see what is the identity theorem. We all of us know the statement of identity theorem is, let D be non-empty connected open subset of a complex plane, and let F be analytic function on D. Then following are equivalent. Option 1, Fz is equal to 0 on the set D. Option 2, the set Z belongs to D such that Fz equal to 0 has an accumulation point in D. Option 3, there exists a point Z0 in D such that Fn Z0 equal to 0, and this is true for all n greater than equal to 0. And the picture would be such type, if f equal to 0 on the set S, then that implies f is identically equal to 0 on whole domain T. That means if given f equal to 0 on any open subset S, then by identity theorem, if D is non-empty simple connected domain, then by identity theorem f is actually identically equal to 0 on whole domain. That means if fz equal to 0 on any open set S, then that implies f is identically equal to 0 on whole domain D. Second concept is, let f and g be analytic on the domain D and S be a subset of D with accumulation point in D. And if f equal to g on the set S, then by identity theorem, if the set has a limit point, means accumulation point in the domain D, then by identity theorem we can tell f equal to g on the domain D. And this is because since we can create a new analytic function such that Hz equal to fz minus gz, which is equal to 0 on the set S. That means if A is equal to 0 on the set S, then by identity theorem we can extend S is identically equal to 0 on whole domain D. This is the identity theorem we all of us know. Today I will see more concept about this identity theorem. First concept, another approach of identity theorem is, suppose f is analytic throughout the domain D and fz equal to 0 at each point z of a domain or line segment which is contained in D, then that implies by identity theorem fz is identically equal to 0 in whole D. That means fz is identically equal to 0 throughout the domain. That means if fz equal to 0 at each point of the domain or line segment contained in the domain, then we can tell fz is identical equal to 0 in whole domain. That means, similar to before, here this line segment which contain in D, consider this is subset S. If fz is equal to 0 on this subset, then we can tell fz is identically equal to 0 on whole domain. This we can define a new function which is going to be analytic for all z in D1 intersection D2. The new function is capital Fz equal to small fz, which is true for all z belongs to D1, and capital Fz equal to gz, which is true for all z belongs to D2. If we can prove that f equal to g for any subset S of D and S contains at least one accumulation point, then we can tell f equal to g throughout the domain D. That means, if f equal to g on this subset, and if consider this subset is S, and if S contains at least one accumulation point, then we can tell f equal to g throughout this interval. And this is the identity theorem we all of us know. But by analytic continuation, we can tell also, if an analytic continuation exists, then it must be unique. That means, if two functions g1 and g2 is managed to be analytic continuation of f to d, that means the picture would be such type. This is d1 and this is d2. If g1 equal to g2, this is the d1 intersection d2. If g1 equal to g2 on the set S which lies in d1 intersection d2, then by analytic continuation we can tell g1 equal to g2, not only this is equal in d1 intersection d2, it is equal in whole d2. That means g1 equal to g2 is equal in d2. This is the analytic continuation. Okay? Means if f is analytic continuation of g from the domain d1 into the domain d2, then the function capital S defined to by equation capital Fz equal to small fz when z belongs to d1 and gz when z belongs to d2, which is analytic in the union d1 union d2, which is the domain consisting all points that lie in either d1 or d2. That means the by analytic continuation, if f is analytic continuation of g from the domain d1 into the domain d2, then the function capital F defined by the equation capital Fz equal to small fz when z belongs to d1 and small gz when z belongs to d2, which is analytic in the union d1 union d2, which is the domain consisting all points that lie in either d1 or d2, and the function capital F is the analytic continuation in d1 union d2 of either f or g. So, by identity theorem, we can tell given a function f and a point z0, suppose that f is analytic throughout a neighborhood n0 of z0. Consider this is neighborhood n0 along the point z0. If z0 equal to 0 and fz equal to 0 at each point z of a domain or line segment containing the point z0, if f z naught equal to 0 at each point of the line segment containing the point z naught, then we can tell by identity theorem fz is identically equal to 0 in whole neighborhood n naught. But by identity theorem we can tell fz is identically equal to 0 throughout the neighborhood n naught. If fz is equal to 0 in this line segment, but f is analytic whole neighborhood, then by identity theorem we can tell fz is identically 0 in whole neighborhood n naught. This is the identity theorem. Now I will see one example. I have discussed this part in my previous video elaborately. Today, just as a review, I have indicate this again. Okay? Let's see one example which had come in CSR Net exam. The example is, the question is, f be an analytic function defined on an unit disk in the complex plane C. Then f is constant if option 1 f of 1 over n equal to 0 for all n greater than equal to 1. Option 2 f of z equal to 0 for modulus of z equal to half. And option 3 f of 1 over n square equal to 0 for n greater than equal to 1. And option 4 imply f of z equal to 0 for all z belongs to minus 1 to 1. First know the identity theorem. Suppose that f is analytic in a region D and f zn equal to 0 where zn is a sequence of distinct points such that zn goes to z naught which belongs to D. Then we can tell f is identically 0 in the domain. That means our approach is, if the limit point of the sequence belongs to the domain, then we can tell f is identically equal 0 by identity theorem. Notice in first option f of 1 over n equal to 0. Since here the sequence is 1 over n and limit point of this sequence stands to 0. So by identity theorem, since the limit point belongs to in the domain, so by identity theorem we can tell f of 1 over n equal to 0 means, by identity theorem we can tell f is identically equal to 0 on this domain. So f is constant function. Option 2 fz equal to 0, and this is true for all z equal to modulus of z equal to half. Here the domain is modulus of z equal to 1 and here given fz equal to 0 on mod z equal to half. Every point of this circle be the limit point. So since the limit point belongs to the set, so we can tell fz is identically equal to 0 on the domain D. So option 2 also right option. Option 3 imply f of 1 over n square equal to 0. Similar to before. Since here the sequence is given 1 over n square and 1 over n square tends to 0 and 0 belongs to D. So by identity theorem we can tell f is identically equal to 0. And option 4 fz equal to 0, this is true for all z belongs to minus 1 to 1. Since in this domain the function is equal to 0, so by identity theorem the limit point of this set is minus 1 to 1, and since limit point belongs to the set, so by identity theorem we can tell f is identically equal to 0. So option 1, option 2, option 3 and option 4 is a right option. Okay? Well, today I will stop here. In my next video, I will discuss what is the Riemann removable singularity. Because in my previous video, I had discussed the essential singularity and pole. In my next video, I will discuss the Riemann removable singularity. And this singularity is very important for higher study. But at first, I will tell you, please see today's video and my previous video of complex analysis. Then my next video will be more comfortable to understand in better way. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.